So we'll now turn our attention to the structure and functionality of the Java semaphore class. And you'll see that this has quite a bit in common structurally with the reentrant lock class that we had talked about previously. Java semaphores implement a variant of counting semaphores. You, of course, could use them as binary semaphores, but they're most commonly used as counting semaphores, where the count can be different from 0 or 1. Semaphore, unlike reentrant lock, does not implement any synchronization-related interfaces. So it's actually not even in the Java util concurrent locks package. It's in Java util concurrent. The constructors give the semaphore a way of being initialized with a given number of permits. And you can see that there's two constructors, and one constructor, as we're going to see here, takes the permits, the permit count, and the other constructor takes the permit count and a flag that indicates the semantics of the semaphore, whether it's a fair semaphore or a not fair semaphore. Now, interestingly enough, and this is actually quite confusing, the count is not a maximum, it's just the initial value. And a lot of people get confused about this and think that the permit count that's given for the semaphore is the max number it can grow to. It's just the number it starts out with. And if you want to learn more about this, take a look at the link at the bottom of the slide. It's honestly a little confusing the way that they've defined it, but once you get used to it, you just will find it not too confusing. But be aware that you can actually have the count bigger than the initial value, although that is probably not a good idea. In fact, and this is even more bizarre, the initial permit value can actually be negative. And what that means is any threads that come along and try to acquire the semaphore are going to block until some other thread or threads actually increment the count so it's greater than 0. And this is also very strange. I have to be honest with you, I've never used an application or written a program that used negative count semaphores, but it's certainly possible. The implementation is structured using the good old gang of 4 bridge pattern, just the way that we had seen the reentrant lock class being done when we talked about reentrant locks. And as we've talked about a number of times now, the bridge pattern is used to decouple the interface from the implementation. And in this particular case, it's so that we can have both fair and non-fair semaphore semantics be supported in a uniform manner. So here's basically the way the implementation works. Again, this is going to look very familiar to you if you remember what we talked about earlier with the reentrant lock. So the locking is handled by something called the sync implementer hierarchy, sync for synchronization. You can see that you have a field called sync of type sync, a little confusing there. And the sync class is actually an abstract class that extends the abstract queued synchronizer. And that's that framework that comes along with Java. It's been there for a long time. And it allows many different synchronizers to implement some core reusable behavior that use essentially wait queues that have various types of first in, first out semantics. And we'll talk more about that in a second. You can also read about it at the link at the bottom of the slide. Then what happens is the implementation of semaphore has a couple of subclasses that extend sync. And one of them is called non-fair sync, which, as the name implies, has the so-called non-fair semantics. And the other is fair sync, which, as the name implies, has fair semantics. And I'll talk about the difference between fair and non-fair semantics in a minute. It's basically the same idea as we saw with reentrant locks. The constructor of semaphore, or one of the constructors, can be used to determine or let the caller determine what semantics are desired. And so if you pass in true for fair, then as you can see here, that'll make a fair implementation. And if you pass in false, it'll be a non-fair implementation, just like reentrant lock. And that should be comforting to see the same pattern used in the same way. And the reason for that, of course, is that the guy who wrote these, which is Doug Lee, is an expert in patterns as well as concurrency and Java and C++ and all kinds of other cool stuff. Fair sync means that we'll emphasize fairness at the expense of performance. And fairness means that the thread that gets the semaphore next when it becomes available is the one that's been waiting the longest. So that's fair semantics. It's like waiting in line at a movie theater or an airport. And non-fair sync basically enables faster performance at the expense of fairness. So things may actually be faster, but they won't be as fair. And so it all depends on what your requirements are as to which one you want to use. By default, the semaphore implementation favors performance over fairness. So if you don't indicate whether you want it fair or unfair by using the 2-parameter constructor, then by default, the 1-parameter constructor just takes the count of permits, will make a non-fair synchronization semantic, which is what you want. Fair sync is generally a lot slower than non-fair sync, so make sure you use it accordingly and perhaps use it sparingly. Only use it when you really need it. So as I mentioned before, when we talked about the concept of semaphores, Java semaphores can either be used in a bracketed or fully bracketed way or a non-fully bracketed way. So in the case that you do the non-fully bracketed model, that means the thread that acquires the semaphore need not be the one that releases it. And as you can see here, when we talk about the ping pong example here shortly, you'll see how that actually gets used. It's kind of fun. So that's the overview of the structure and functionality of Java Semaphore. At this point, you really don't have enough information to program them with any degree of accuracy, but we'll cover the methods here starting with the next lesson.